In modern households, batteries are embedded in everyday life in ways that are often overlooked. From automotive systems and backup power units to cordless tools, emergency lighting, laptops, and renewable energy storage systems, batteries function as distributed energy components within the home. As the number of battery-powered devices continues to expand, so does household reliance on stored electrical energy. In recent years, residential energy systems have become more complex. Solar panel installations, small-scale wind systems, and hybrid energy setups increasingly incorporate battery storage as a core element. Even in homes without renewable systems, battery backups for outages and portable power stations are common. As a result, the life cycle of batteries has become a practical consideration in home energy management. However, batteries are consumable components. Over time, they degrade due to chemical reactions, sulfation in lead-acid systems, charge cycle limitations in lithium-ion units, and general wear from environmental conditions. When performance declines, many households treat batteries as disposable items. Automotive batteries are replaced every few years. Rechargeable tool packs are discarded when capacity drops. Smaller household batteries are routinely thrown away. This pattern contributes to rising household expenses and increased material waste. Batteries contain metals, electrolytes, and manufactured components that require energy-intensive extraction and production processes. In sustainability discussions, attention is often given to renewable generation technologies, but less emphasis is placed on extending the operational lifespan of storage systems. Battery reconditioning emerges within this context as a technical practice aimed at restoring partial functionality to certain battery types. It is not a new concept. Historically, technicians and mechanics routinely attempted to revive lead-acid batteries through maintenance procedures. In off-grid and industrial environments, battery servicing has long been a recognized skill. As interest in sustainable home energy grows, battery lifecycle management has re-entered the conversation. Rather than viewing batteries solely as replaceable units, some households explore maintenance and restoration methods as part of broader resource efficiency strategies. When batteries begin to lose performance, most households follow established patterns. The first and most common approach is full replacement. Automotive batteries are exchanged at service centers. Rechargeable tool batteries are replaced with manufacturer-approved units. Laptop or phone batteries are swapped through authorized repair services or upgraded entirely through device replacement. A second approach involves basic maintenance practices. For lead-acid batteries, this may include checking electrolyte levels, cleaning terminals, ensuring proper charging cycles, or maintaining recommended storage temperatures. For rechargeable household batteries, users may attempt calibration cycles or control discharge and recharge sequences. Some individuals attempt simple revival methods found in online forums. These might include slow charging techniques, desulfation pulses for certain battery types, or voltage equalization attempts. In limited cases, hobbyists experiment with basic conditioning chargers designed to balance cells or restore partial capacity. In renewable energy households, battery banks are often monitored through charge controllers and energy management systems. These systems may include automated equalization settings intended to reduce sulfation buildup in lead-acid configurations. These approaches represent the most accessible and widely known responses to declining battery performance. While common methods can address minor performance issues, they often face technical and structural limitations. Battery degradation is rooted in electrochemical processes. In lead-acid batteries, sulfation occurs when lead sulfate crystals harden on the plates, reducing the surface area available for chemical reactions. In lithium-ion systems, degradation can result from electrolyte breakdown, thermal stress, or internal resistance increases. Not all forms of degradation are reversible. Standard consumer-level maintenance techniques typically address surface-level issues rather than deeper chemical imbalances. Basic charging adjustments may temporarily stabilize voltage output, but do not necessarily restore lost capacity. Replacement remains the dominant solution because it offers predictable results without requiring technical intervention. Additionally, modern batteries are increasingly sealed and engineered for minimal user servicing. Unlike older battery models, which were designed with accessible cells and maintenance ports, many current units limit direct intervention. This design shift reduces the practicality of traditional servicing techniques. Safety considerations also influence outcomes. Improper handling of batteries can present risks, including short circuits, chemical exposure, and fire hazards. As a result, many households avoid experimental procedures and default to replacement. In renewable energy systems, battery banks are often integral to system reliability. Homeowners may prioritize stability over experimentation, especially when energy independence depends on consistent storage performance. These structural factors contribute to the widespread perception that battery failure equates to end-of-life status, even in cases where partial restoration may be technically feasible. Within sustainability and energy efficiency fields, alternative perspectives have developed around battery lifecycle management. One perspective focuses on circular resource principles. Rather than treating batteries as single-use components, this view encourages examining whether controlled restoration methods can extend usable life. The goal is not necessarily full capacity recovery, but incremental extension of functional service. Another perspective emerges from off-grid and remote environments, where access to replacement batteries may be limited. In such contexts, maintenance and conditioning practices become practical skills rather than optional techniques. Technical communities have also explored desulfation technologies, controlled reconditioning cycles, and voltage balancing strategies as part of broader system management. In certain battery chemistries, specific restoration procedures can address imbalances or performance inconsistencies under controlled conditions. Educational discussions in sustainable home energy increasingly frame battery maintenance as one component of overall system literacy. Just as homeowners learn about inverter sizing, solar array positioning, and load balancing, battery chemistry and maintenance are becoming part of the broader knowledge base. Importantly, alternative perspectives do not position reconditioning as universally applicable. Rather, they examine it as a contextual tool within resource management. In some cases, restoration may offer marginal improvements. In others, degradation may be irreversible. The conversation continues to evolve alongside advances in battery technology and home energy integration. Within this broader discussion, structured educational materials have emerged that focus specifically on battery restoration practices. One example is the new battery reconditioning course, which is presented as a step-by-step instructional resource addressing different types of rechargeable batteries. The course material is described as covering general methods related to battery reconditioning processes, including automotive batteries, certain deep cycle systems, and smaller rechargeable units. It functions as an organized guide that compiles procedures and technical explanations into a single reference format. In the context of sustainable home energy discussions, resources of this type are positioned as educational tools that explore restoration techniques within defined parameters. They represent one category of informational material within the broader field of battery maintenance and lifecycle management. Battery reconditioning as a home energy practice exists within a larger conversation about resource efficiency, system literacy, and lifecycle awareness. In some households, battery replacement remains the standard response to declining performance. In others, maintenance and restoration methods are explored as part of sustainability-oriented practices. Approaches vary depending on battery chemistry, system design, technical familiarity, and individual priorities. Not all batteries are suitable for restoration, and outcomes depend on multiple factors. As residential energy systems continue to evolve, discussions around battery management are likely to expand. Understanding the underlying principles provides context for evaluating different approaches. This content is intended for informational purposes only.